Hello everyone. Haven't done a video in about a week or two now, but I think that's because we've probably been doing topics that were quite complex, and also the fact that there was a lot of content to cover. So I think now that your teachers have probably gone through some of the main stuff and you get the basic concepts, we can now apply these skills to a real life application. So today we're going to be exploring stationary points and their applications. And to do this, we're going to be working on a question from 18E. So I'm going to, question 4 to be exact, and I'm going to explain what these stationary points are and then how we use them in the real world in this application. So let's say we had a graph here, and the equation for our graph was something like, and this is direct from the question again, 36x minus 24x squared plus 4x cubed, and obviously that'll be y equals there. So if we were to graph this in something like Desmos, at x equals 1, we'd get a point of 16 up here. So this is 1, 16. And at x equals 3, let's say that's over here, we'd get a point of 3, 0. So if we were to draw this graph, and I'm not going to do the negative sides, you can put that in Desmos if you really want to see that. It would go up like this and down to there, and it would start to go up again. So what we have here, these 2 points where you can almost draw a straight line across them and the gradient is equal to 0, are called stationary points. So that means if you were to find the derivative of this function, so this function here, if you were to find the derivative of this and insert that x value, you would get an answer of 0. So let's try that now. Let's find the derivative here. So y apostrophe, this apostrophe just denotes a derivative. So if you see that apostrophe, that means you're figuring out the derivative. And we're going to work through here. So the rule for a derivative, as discussed in the live stream, if you were on it, I'll do a little example on the right hand side here so that you can see how to solve a derivative. Let's say we had 3x squared. So you've got your coefficient out the front here. This is your coefficient. And you've got your exponent up the top here. So let's say we had a, so a was our coefficient, x, n. So the rule for this, if you were to find, let's let this equal q equals ax to the power of n. If you were to find the derivative of q apostrophe, again, that's how you denote it, what you need to do is multiply n by a, x to the power of n minus 1. So if you had 3x squared, again, let's let that equal q apostrophe, or the derivative of q, would equal 2 times 3 x to the power of 2 minus 1, which just becomes 6x. So 2 minus 1 is 1, so you just leave the x. You don't have to put the 1 up here. So just get rid of that. Alrighty, so let's go back to our graph now. We're going to find the derivative of y. So we're looking back over this side. The derivative of y equals, so 36x, that's the same as 36x to the power of 1. So we do 36 times 1, so we get 36 out the front, and x to the power of 1 minus 1 is x to the power of 0, which is equal to 1. Anything to the power of 0 is equal to 1, so x to the power of 0 becomes 1, so you just leave this as 36, the x is removed. We'll then go through these next ones. So you have negative 24 times 2, so negative 48x. That 2 becomes 1, so you just leave it as x. And the final one is 12x squared. Hopefully you're following along with where these numbers are coming from at this point. If you don't get it, go back to this explanation here, maybe rewatch it. So let's now solve a problem with this. So let's say we had a square like this, or a box rather, an open box, so it hasn't been folded yet into a box. And this length, let me get a different color here. This length here is equal to 6. And a square, so a square was cut out of each of these corners with a length of x. So this white, the white border that I've drawn here is the shape we have. The blue is not part of the shape, so just ignore that, but I'm just showing you where the x value would be, or where that dimension is. So we know that if that x is there, this will be x, this will be x, and also that will be x, because it's a square. So let's now work through this problem to figure out the maximum volume of this box. So we know that the volume of a rectangular prism is equal to length by width by height. In this case, the length and the width here are the exact same. So we have V equals length squared times h. Now that we know the length, the white bit here of this box, again the 6, that green line is not the shape, so the white is just the shape, so that we know the length of the shape is equal to V, so V equals the length, so 6 minus 2x, so we have an x on each side here, so we're going to minus 2x to get, let me just redraw that x, that's pretty crappy, to get the length of this side. And then we're going to multiply that by the height, which in this case is x. So if we expand this now, we get v equals 6x minus 2x squared. We're then going to go back to factorizing this up here. So let me rearrange this as y apostrophe equals 12x squared minus 48x plus 36. Now you might see from a previous video, you might see that this value out here is a, this one is c, and this one is b. So what do we do when we've got those three variables? We use the grouping method. Grouping method. Let me get that in. Alrighty. So first thing we're going to calculate is AC for the grouping method. Now if you don't understand this, go back to the solving limits and factorization tutorials. Skip to a few minutes in, you'll find the grouping method. It's written pretty clearly if you want to have a look over that. So AC in this case is equal to 12 times 36, which I've got here as 432. So we're then going to find factors of 432 that add to negative 48. In this case, we've already actually got them, the 12 and the 36. So we write this as y apostrophe, the derivative of y, is equal to 12x squared minus 12x minus 36x plus 36. And we're then going to group these two sides. So there's blue lines each side. So we have y apostrophe equals, we've got to find the highest common factor of this first side here. So the highest common factor of those two terms are 12x. So 12x multiplied by what equals 12x squared, that's x. And 12x multiplied by what equals negative 12x, and that's negative 1. We then do the same for this other side, the highest common factor of these two. Usually, if you've got a negative as this if you've got a negative out the front of this first term, you know that you need to get a positive for this one. So a negative times a negative equals a positive. Therefore, we're going to keep the negative out the front, and you'll understand this in a second. When we multiply it by x minus 1, remember we want these two to be the same. So if we do negative 36 times x minus 1, we get negative 36x plus 36, which is equal to this. So if you've got that negative before the 36x, you want to keep the negative out the front and make sure that these two terms inside the brackets are the same. We can then further factorize this by collecting these two terms now. So we have 12x minus 36 multiplied by x minus 1. We then use the null factor law to figure out the x values for both of these. So 12x minus 36, we move that 36 to the other side. So let me just write these two equations out so you understand what I'm doing. 12x minus 36 and 0 equals x minus 1. So if we move that to the other side now for the first, so let's have this as equation 1 and this is equation 2. If we do equation 1 here, we can move the 36 to the other side. So we get 36 equals 12x. Divide both sides by 12. This is just basic algebra. This shouldn't be too challenging for you. And we get x equals 3. The second one, 0 equals x minus 1. Move the x to the other side, and we get x equals 1. You would have done that many times before, so that shouldn't be any trouble. Now let me scroll down here, and we can keep working through it. Obviously, I'm doing these steps quite documented. You might do this a little bit quicker in your own time, but I'm just trying to explain what all of this is from. So hold on, let's scroll back to the graph here. And you can see that when we graphed this originally, we had 1 as one of the x values. So top left of the screen is where you're looking. 1 was one of the x values, and 3 is one of the x values. And as a matter of fact, that is what we have found down here. X equals 3 and x equals 1. And those points are the two stationary points. So these two stationary points are the same as the turning points, or they can also be point of inflections. I can discuss those in another video, but don't worry about them now. So at x equals 1, up here on the graph, we had a y value of 16. So because that's the highest point in the graph, we call that a maximum. And at x equals 3, it's 0. Therefore, we call that a minimum. So if we move back down now, one thing to note is this graph also may continue past the negative, down past the x-axis. So sometimes this could be a min, or sometimes it could be a point of inflection. It depends where you're, like what domain of the graph you have. But don't worry about that now. All you need to know is that at x equals 1, we had a value of 16, and that's the maximum point of our graph. Therefore, we can solve for the volume. We know that at x equals 1, the volume, V, is equal to 16. So you can see we went through all of that working to figure out the maximum volume using calculus of a box.